5-2, polynomials, linear factors, and zeros. So in this section, we are going to, my objectives are to analyze the factored form of a polynomial and to write a polynomial function from its zeros. And my essential understanding is that finding the zeros of a polynomial function will help you factor the polynomial, graph the function, and solve the related polynomial equation, which we will, of course, get to. So, in Chapter 4, we solved a quadratic equation of the form x squared plus bx plus c equals 0. We solved it a bunch of different ways. The first and the easiest way was by factoring. Then, if you remember, we also solved it with grouping, and we solved it using the quadratic formula. So, for now, we're going to stick with factoring, however, in this section. We wrote it using linear factors in the form of x minus r1 and x minus r2. So we had two sort of numbers that multiplied together and combined to give me the trinomial that I started with. We then applied the zero product property to find my solutions of whatever number r1 happens to be and whatever number r2 happens to be. We set both pieces equal to 0 and solve for r1 and r2, whatever they were. We can solve some polynomial equations now. Remember, this is a polynomial function in standard form. We can solve some of those equations in exactly the same way by factoring out, by taking out common factors first, and then factoring what's left over like a quadratic. And then what we'll do next time in the next section is set those pieces equal to 0 so that we can solve the related equation and we can figure out the zeros of the function. So let's start with an easy one. What is the factored form of x to the third minus 2x squared minus 15x? So you should notice first that all of these have a common factor. They all have a common factor of x. So start by taking out the x. We're left with x squared minus 2x minus 15. And then we can continue to factor and find the factors of 15 that subtract to 2 to give me x minus 5, x plus 3. And that is my factored form. If I wanted to, I can check this by multiplying these two together using FOIL and then taking my answer and multiplying them all by x. But it is right. Okay? So that leads us to remember that how these things interact, okay, with roots, zeros, and x-intercepts. So the following are equivalent statements about a real number b and some polynomial p of x is equal to my polynomial in standard form. So what is true about these? Well, the first little dot there says that x minus b is a linear factor. So that means that if we have a linear factor, and we know it's a linear factor of my polynomial, not only is x minus b a linear factor, but b is a 0 of the polynomial. B is a root or a solution of the polynomial equation if I set it equal to 0. And b is an x-intercept of the graph, y is equal to p of x. So you should have realized this by now, especially in Chapter 4, that a lot of these things mean the same thing. If I have a factor, that means I know the 0, I know the root, I know the solution, I know the x-intercept. All of those things mean the same thing. All we have to do is find the factors. Once we find the linear factors, right? Once we find the linear factors, we can then use them to figure out a lot more information about the polynomial function. And that would actually help us graph it if we wanted to. Okay? So we don't, even though we don't do a lot of graphing, let's try to graph this one and be sure that we know what these things mean. So first it asks us, what are the zeros of this polynomial function? Well, it's easy to find the zeros because it's written in factored form. As we go forward in the chapter, we'll figure out how to turn these cubics or quartics into factored form. But for now, we have it in factored form. My zeros are easy. So that means that x is going to equal -2 with that factor right there, setting that equal to 0. X is going to equal to +1 with this factor. And then x is going to equal to 3 with this factor right here. So based on that, we can then start to graph this function. So let's plot those 3 points. And remember that because they're zeros of the function, it also means that they're x-intercepts. So that means that I can take those 3 points and put them onto my graph at -2, at 1, and at 3. Well, not really enough information yet to graph this function, so I'm going to need some more points. So in order to get some of these points, let's make a table. So, okay, I already know that at -2, 1, and 3, that my function is going to be equal to 0 because that's what it means to be a zero of the function. So let's try a couple more. Let's try -1. Let's plug in 0. And let's plug in 2, which I pick those because those are sort of points in between the 3 points that I have right here, -1, 0, and 2. And if I can plot the graph at those points, I can maybe have a better idea about what's going on. All right, so plug in -1 into my function. Remember, I have to plug it in at all 3 spots. That's going to be -1 plus 2. That's going to be a 1 times a -2 times a -4, which is going to be 8. At 0, 0 would give me a 2 times a -1 times a -3, which would be a 6. And that would be 4 times 1 times -1, which would be -4. Okay. If you're not sure where I'm getting these numbers from, all I'm doing is taking 2 and I'm plugging it into all 3 of these. Plug 0 into all 3 of these. Plug -1 into all 3 of these and multiply them all together. Okay, so now I have a couple more points, which I can then graph. So -1, 2, 3, 4, 5, 6, 7, 8. Oh, excuse me. 0 and 6. 1, 2, 3, 4, 5, 6. And 2 and -1, 2, 3, 4. All right. So now I should have kind of a better idea about what this function looks like. Remember back to last section when we talked about end behavior. Okay? If I happen to know the lead term of this polynomial, which I can figure out by multiplying all these first terms together, and x times x times x gives me x to the third. So looking at that, I know that my lead term is positive, and it has an odd exponent. So having a positive and odd lead term means that that n goes down, and this n goes up based on the end behavior. So now, with this in mind, I can make a rough estimate, like a rough estimate of this graph. So let's sketch it. I know that it can only cross the x-axis at its 3 zeros, and that it's got to go through all those other points, and that it has to be a smooth curve, and that the left end has to be going down and the right end has to be going up. So with that in mind, I can get a graph that looks kind of like that. Now, is that exact? Not really. If I wanted an exact graph, I could plug it into a graphing calculator or into my Desmos app. So let's talk next about the factor theorem. Okay? The factor theorem describes the relationship between the linear factors of a polynomial and the zeros of a polynomial. It says the expression x minus a is a factor of a polynomial if and only if the value a is a zero of the related polynomial function, which should make sense. Because if I have this as a factor, if I set it equal to 0, it would be a 0. So that is useful because now if I have factors, I can get zeros. And from the other way, if I know the zeros, I can write the factors. So writing a polynomial function from its zeros is pretty straightforward. What is a cubic polynomial function in standard form with the zeros -2, 2, and 3? Well, if it has a 0 of -2, that means it has to have a factor of x plus 2. Because if I set that factor equal to 0, I would get an answer of -2. It also has a factor of, it also has a 0 of 2, which means it has a factor of x minus 2. And it has a 0 of 3, which means it has a factor of x minus 3. So that's my polynomial function. Unfortunately, that is not written in standard form. So what we're going to have to do is we are going to have to multiply these together and put them into standard form. Well, I'm going to start with these two because I should remember from factoring quadratics that those are going to produce the difference of perfect squares. Or I can remember, I could FOIL this. X times x gives me x squared minus 2x plus 2x, which are going to cancel out, and then minus 4, which I should recognize as the difference of squares. And then I'm going to have to multiply this by x minus 3. Now I'm going to use FOIL, or my double distributive property. X times x, x squared times x gives me x to the third minus 3x squared minus 4x plus 12. And that is my polynomial function in standard form. And it has zeros of -2, +2, and 3, which would be hard to tell just by looking at my expanded form right there, standard form, and we'll get to see, actually, we'll get to how to figure out the actual zeros in a later section. But for now, we're just going to write the zeros and we're going to multiply them together. What about this one? What is a quartic polynomial function with zeros of -2, -2, 2, and 3? So let's do the same thing. Let's make here are my 4 zeros. Okay, let's turn them into my 4 factors. So that would be, the first one is going to be x plus 2. The second one is x plus 2 again. The next one is x minus 2. And the last one is x minus 3. Okay, and so those 4 zeros produce those 4 factors. Now, unfortunately, it is not in standard form again, so I'm going to have to multiply these out. From the previous problem, you should recognize that. So I can easily multiply those two together to give me x plus 2, x squared minus 4, which is those two factors multiplied together, and x minus 3. Okay, so now we have a couple choices. We can multiply however we want to do this. I'm going to multiply the first two together and then multiply it by the third one. So we have y is equal to x to the third minus 4x. I'm going to actually put this over here because I'm going to keep this in standard form, plus 2x squared, and then a minus 8. And I'm going to take all this and I'm going to multiply it by x minus 3. Okay, which means that I can't think of it quite as FOIL. We have to think about it as more distributive property. I'm going to take every single one of those terms and I'm going to multiply them by x and then by -3. Okay. All right, so x to the third times x is going to give me x to the fourth. X to the third times -3 gives me minus 3x to the third. Okay, and then we're going to take the 2x squared and multiply it by both of those as well. Gives me 2x to the third minus 6x squared. Multiply those, gives me minus 4x squared plus 12x minus 8x, and finally plus 24. And now you notice that there's some terms that are alike. So all I'm going to do is I'm going to add those like terms together. So we have x to the fourth, because that doesn't combine with anything. These two go together to give me minus x to the third. Of course, remember, when we combine things that have the same exponent, only the coefficient in front changes, not the exponent. Minus 6x squared minus 4x squared gives me a minus 10x squared. Plus 12x minus 8 gives me a plus 4x and a 24. So that is my fourth degree polynomial in standard form that I have gotten from these four zeros, from -2, -2, 2, and 3, and multiply them together. Okay. Let's compare the two graphs. Okay. So I've graphed these previously in Desmos, and we can see that both graphs have similar zeros. Right? If we look at my zeros, right, this quartic had had -2, -2, 2, and 3, and the cubic had -2, 2, and 3. So both of these graphs cross the x-axis, or both of these graphs have the same zeros. But notice the difference. Well, first of all, this one is a cubic. It has a positive lead coefficient and is odd. So my graph is going to go down, then up, down, and then up, which it does. This one has a positive and even, so that both ends go up, which they do. The biggest difference is what happens right here, right? In my first problem, in my part A, the 0, -2 happened once. In this one, it happened twice. And look what happens. At that 0, the graph just touches the axis and goes the other way. At the one right here, this graph goes through the x-axis. And every other graph, the graph goes through the x-axis at those zeros. The 0 here in this function at -2 is the only one where the graph does not actually cross the x-axis. It touches the axis and goes the other way. This is a special situation. So if we look at the factored forms as in my first problem, +2 - 2 - 3, which we started with, and in my second problem as x + 2 squared, because it happens twice, in the second problem in part B right here, okay, x + 2 makes -2 a multiple 0. It happens more than once, okay? And we can see that this 0 happened more than once. It happened twice. So that makes that has a special name. Since the linear factors twice, you can say that -2 is a 0 with a multiplicity of 2. So instead of writing that, if we were going to write out the factors, or write out the roots, instead of writing it -2 twice, like it did in the problem, we would say -2 with a multiplicity of 2. In general, A is a 0 of multiplicity n means that that factor appears n times. So if we say 2 is a multiplicity of 3, that means that the factor x - 2 would happen 3 times. Okay? And an important thing to notice is that if A is a 0, this is how these multiple zeros affect a graph. If A is a 0 of multiplicity n in the polynomial function, then the behavior of the graph at the x-intercept A will be close to linear if the 0 happens once, if n equals 1. It will be close to quadratic if n equals 2. If the 0 happens twice, it'll be close to cubic if n equals 3. And we could see that in these graphs right here, which all three of these zeros happen once. So these zeros cross the x-axis kind of like a line. These two zeros both happen once. the graph crosses the x-axis kind of like a line. But this 0 happened twice, which means that the graph touches the x-axis and goes the other way, kind of like a quadratic. And if the 0 happened 3 times, it would look kind of like that, kind of like a cubic. Okay? So that's how multiplicity, multiple zeros affect a graph. So if we were going to look at this, what are the zeros of that function? What are their multiplicities? How does the graph behave at these zeros? Well, the first and easiest way to figure out the zeros is to actually factor it. So let's factor that equation to start. They all have at least an x squared in common, so let's take that out, which leaves me with x squared minus 2x minus 8, which I could then factor even further to be x minus 4, x plus 2. And I can think of x squared as x times x, okay? Which tells me that the zeros of the function are x equals 0 for both of these. So that 0 has a multiplicity of 2. Okay? Next, x is equal to 4, and x is equal to negative 2. Okay? So this tells me that my graph will cross the x-axis at both of these points, at 4 and at negative 2. But something special happens at 0. The 0 of 0 happens twice because I have x squared. I have 2 x's there. So the 0 happens twice. So that means the graph is going to touch it's going to behave like a quadratic. It's going to touch the x-axis and go back the other way. Looking at the picture, I can see that at negative 2, the graph acts like a line. At 4, the graph acts like a line. But here, at 0, the graph acts like a parabola, and it touches the x-axis and goes the other way. Okay. So if a 0 happens more than once, right, we can determine how that will actually affect the graph. So if the graph of a polynomial function has several turning points, the function can have a relative maximum and a relative minimum. A relative maximum is the value of a function at an up-down turning point, and a relative minimum is the value of a function at a down-to-up turning point. And these should be kind of obvious. Maximums are just peaks of a graph, and minimums are valleys of a graph, right? Where the graph is at a top or where a graph is at a bottom and it changes direction. I should also realize that since this particular graph has 2 turning points, it at least has to be something to the 3rd power. Remember that. And my leading coefficient must be negative because this end goes up and this end goes down. So even though that's not really what we're talking about here, don't forget about all the stuff that we have learned previously in regards to polynomials. So, identifying relative mins and maxes. What is the relative minimum, maximum, and minimum of that graph? There is no easy way to calculate that. Basically, what you're going to have to do is you're going to have to use a graphing calculator or Desmos. So when we look at this polynomial that's plotted out, I can tell that it does have a relative maximum and a relative minimum. The relative maximum is here. The relative minimum is at this point right here. And I can tell that easily from the graph. These 3 points I could also figure out by factoring that polynomial to find this 3 zeros. Okay. So when we get a problem that looks like this, a nice word problem, you can solve it using a graphing calculator or Desmos again, but you're going to have to change the paragraph into some sort of formula. So let's look at it. The design of a digital box camera maximizes the volume while keeping the sum of the dimensions at 6 inches. If the length must be 1.5 times the height, what should each dimension be? Okay, so I know that in order to find volume, I need length, width, and height. Let's call height x, which means the length is going to be 1.5 times x. And now let's put the width, right? I don't know the width yet. Let's put the width in terms of x so I can make a nice equation. Well, I know that the sum has to be 6 inches. So that means that length plus width plus height is going to be equal to 6. I know that length is 1.5x. I know that height is x. Putting those together gives me 2.5x plus the width is equal to 6. So that means that the width is equal to 6 minus 2.5x. Replacing, substituting right there. I now have a formula for volume. My formula for volume is going to be 1.5, well, let's start with x. X times 1.5x times 6.6 minus 2.5x. Length times width times height equals volume. So now we have 1.5x squared times 6 minus 2.5x. And then I'm going to FOIL this, multiply it all together, write it in standard form, and I'm going to get a formula of negative 3.75x to the third power plus 9x squared. Now that I have the formula in standard form, I can plug it into a graphing calculator and solve. Now, I know I don't care about any of those numbers because those are negative x's. And if x is going to be height and it's going to have something to do with length and width, I can't have negative numbers. And so I want to see where this graph has a relative maximum, which is right there, which means that x is going to be 1.6. Plugging it into the other, so this is going to be 1.6, which would make my width, well, this would be then 2.4, and this would be about 2. Okay. And that is 5-2, polynomials, linear factors, and zeros.